What's up there, guys? Thanks for tuning in. I'm Rick. This is Fanfare for the Conscious. And in the video today, Left Brain Spirituality Part 5, Dimensionality. Let's dive in. So if you're one of those people that normally only watches a few minutes of these videos, I would implore you just to stick around this time and accept that even if a lot of this information kind of makes your head spin and possibly some of the language is a little bit over you, just try and let the information wash over you, because I've come to understand a lot of this information over many, many years, and it is quite a deep level of understanding that we're going for here. And even if you don't necessarily fully comprehend what it is that I'm talking about right now, you may find that with a little bit of time to digest it, and a little bit of time to unpack the information, and a little bit of time to integrate that information into your worldview, that this information itself is very, very important. And maybe something that doesn't make sense to you now might then click with information that you get later. So give it a chance and let it wash over you, and let's see what happens. So today's Left Brain Spirituality Part 5, Dimensionality, and we're going to be covering vortices, vibration, and the wave-particle duality here. And this is all approaching describing matter itself as being standing waves of light. But if we want to be able to explain this to our left brains, then we need to give it a little bit more context. So we're going to talk first about dimensionality. Now, dimensionality is a feature of a property having a linear degrees of difference. Now, I know that's a bit of a complicated sentence, so I'm just going to say it one more time. It's the feature of a property having linear degrees of difference. And what does that mean? Well, if you were to graph the differences in that property, there is a linear change that goes in a measurable direction. So height goes, linearly along its scale. Weight goes linearly along its scale. All these things have, a linear structure to the property, so to speak. So things like spatial dimensions, height, width, depth, length. Temporal dimensions, so you've got time, the whole concept of time being a linear measure as well. You can also think of time itself as a linear dimension. Admittedly, we're only limited to moving along that dimensional plane in one direction. However, you can consider it to be a form of dimension. And then you've got conceptual dimensions, like the dimensions of passion, from love to hate, and the dimensions of interest, from being very interested to something to being not at all interested. You're talking a linear scale along a single axis of a graph, so to speak, and that's an idea of dimensionality. And they're necessarily polar in nature, and it's a variation between two extremes, either an extreme positive and an extreme negative, or an extreme of nothingness to an extreme of somethingness. So having zero width or length or height or whatever, versus having a length or a height or a weight. So that's the idea of dimensionality, and we can sort of, look at here the idea of building up in dimensions. Now, we're literally talking about, with these various diagrams here, there not being any sense of time, because time in itself would be an extra dimension. So when you're thinking of the universe as being three-dimensional, well, it's not. It's four-dimensional. You can talk about other layers of dimensionality beyond that. You can add an electromagnetic dimension to that, and there's all sorts of other ways of considering dimensionality. But in terms of the way we experience it, it's four-dimensional. We've got three physical dimensions in which we can move, and then there's one temporal dimension through which we are carried, so to speak, without our will. So a zero-dimensional entity would be a single point. And when I'm talking about a single point, I'm not talking about a full stop or a ball. I'm talking about a point with no, dimensions to it whatsoever. It's just a thing that doesn't have any real structure or any measurable components to it. And that's the thing on its own without any dimensionality. It's just a thing. When we start to give that a bit of structure, we get your first dimension, which you can think of as a string. It has no width, it has no height, but it has a length. So it's got starting to gain some form of substance now because it has something that you could measure. Two-dimensionals, you could get a square, or you could also think of a circle. Circle would be the female representation of two-dimensionality, which is that string curved around on itself, whereas the square is the doubling of that string in two separate dimensions and forming a plane, a flat plane as you'd consider it. You might have length and width, but you're not going to have any sense of height or depth or thickness whatsoever. It's a single flat, infinitely thin plane. When you start to add the third dimension, though, this is where we get volume, and this is where we start to get the three-dimensional structure of the reality through which we move and are moved through in time. And there is the fourth dimension. You could also have a fourth physical dimension, so to speak, and that would be something called a hypercube. And I suppose you could also have a hypersphere. But I can't draw a hypercube. I did have a go. The other name for it is a tesseract. And what I'm going to do is I'm going to show you the best way that you could even attempt to draw this. Because don't forget, when I'm drawing this cube here, we've got a three-dimensional object being represented in two-dimensional space. I don't actually have a cube to hold in front of you, which would be the three-dimensional object represented in three-dimensional space. I'm not sure if there's any actual structures you can get. You might be able to find them out there on the internet, three-dimensional hypercube structures. But I'm going to play you what is considered to be the best two-dimensional representation of a four physical dimensional object. So this has some fourth physical dimension that object extends into. And what you're seeing up there obviously isn't the object, because it would be impossible for you to conceive of what it is as a shadow of that object if you just imagine the given lines of the borders of that object, so to speak. So now we're going to come along to vibration. And a vibration now is an oscillation between two different extremes of a pole. So an oscillation between north and south extremes in terms of a magnetic oscillation, or two different extremes of oscillation in a wave. The height of a wave would be considered to be, part of the oscillation of that medium. And it requires a minimum of two different dimensions. So you can't have an oscillation with a single dimension. You can only have an oscillation when you have two dimensions, because you need one spatial dimension in the examples I'm going to be using, though it could be any other sort of dimension, and you need one temporal dimension, because there has to be variation in whatever medium you're measuring over time. And this is where we come into what waves actually are, and what we covered in the previous video is an oscillation of a medium, and this is where you get a vibration, which is also a wave, or can be represented as a waveform. So we've got vortexes. Now, vortexes are an inward or outward spiral motion of a fluidic medium. And this is important when we're actually considering what goes on with a wave, when considering it as a fluid medium oscillation. We'll come into that a little bit more later. And then we also have the wave-particle duality, which is the tendency of photons, subatomic particles, and indeed matter itself to exhibit both wave and particle-like properties. Now we've got the sort of basic ideas of how dimensionality and a vibration vortexes and wave-particle duality work. We can start to try and put them all together to understand how do we get a particle forming when in reality just an oscillation of a fluid medium. So let's start and have a look at just this basic two-dimensional waveform. We've got one spatial dimension or conceptual dimension, and you could call it a potential, potential for difference between two extremes. And then you've got that potential difference between the two extremes changing over time. So in this example, we've got an oscillation from a base level of 0, which is where the medium itself is not oscillating at all. This is where the idea of a 0 point field comes from. There should be no oscillation at that 0 measurement, though we find it. Oscillates from 0 all the way up to the maximum positive, or to the extreme positive of this particular waveform, then goes back down through the 0 point and then back into the negative end of the waveform. So again, you can see this sort of wave, and you can imagine this oscillation of a medium between two different extremes of the waveform. So let's see if we can start to make this into an object. So you can imagine a single point. If we were doing this in only 2 dimensions, you can imagine a singularity moving, so there's 0 dimension, a single point moving all the way up and all the way down, so along a height dimension, shall we say, over time. So it would start at the midpoint of its travel, go up towards the top, and then it would come down towards the bottom. Now, that isn't an easy thing to imagine, because you've got to see that this thing is slowing down as it gets towards the top. The change in potential in a waveform, a traditional waveform, is curved. So initially, the change is quite rapid, but as it gets towards the top, the change slows down and slows down and slows down until it reaches the peak. Then it starts to slowly fall, and that fall then increases and increases and increases. So this point is actually slowing down as it gets towards the top. So is there an easier model, the one that accounts for more of these features of the waveform? Well, yes. We could imagine that maybe we're looking at this circle from the side instead, and we flip it over. Imagine that thing turned that way and put in front of you. Now we've got a structure that is actually modelling very easily what that waveform is. And what we're starting to get is this vortex effect, the spiralling motion of the fluidic medium. Now, if we start to look at what electromagnetic waves are, light, you've got oscillations of 2 separate waveforms. You've got the change in electrical charge, and then you've got the corresponding magnetic charge. There's always 2 different field forces being at play here. Remember, whenever you've got a changing electrical field, that necessarily produces a changing magnetic field, and vice versa. The 2 are intrinsically linked. Wherever you get this changing electrical current, this changing charge, you will necessarily get a change in magnetic charge. So this can actually be considered to be a single waveform oscillating in 2 different dimensions. So we've got 2 dimensions of change, and now we've got 1 dimension over which we're measuring that change, the linear time. So we've got a 3-dimensional object now. And remember, this can all be measured by a single waveform. We don't actually need these 2 because one implies the other. And you'll see I've done these slightly staggered, but that's because it was the only way to get a flat 3-dimensional representation of that current without drawing some really strange objects. So here we go. We can see the electric potential potentially is changing. We can see that the electrical potential is changing, and as that rises, you can follow this point moving up towards the top and then moving down towards the bottom. That green line moves towards the top, that green line moves towards the bottom. Oscillations up and down from that neutral axis. See that green line across? That's the neutral position. So it goes from the neutral position to the extreme height, from the extreme height back to the neutral position. There we are. And it goes from the neutral position again on the other side, because again, this green line is only measuring 1 dimension. It's only measuring that up-down. It's not measuring the side-to-side, just measuring the up-down. So that spot then moves from that neutral back down to the extreme low, and then all the way up to the neutral once again. So we're getting that idea of oscillation. That blue line then is not representing the up and down anymore, but what it is doing is representing the side-to-side motion. It starts at the extreme left, goes up to the neutral position, goes down to the extreme right, back down to the neutral position, and from the neutral position back to the extreme left. So that combined waveform there has represented a three-dimensional object. You can think of this either as a tube, you can think of it as a tube, or as a sphere rotating in a single axis. But what if we want to create a four-dimensional object? Now remember, four-dimensional object is the thing that actually exists in three-dimensional space, because you need three dimensions of change and you need one dimension over which to measure that change, which is time. So this object has both height, it has width, and it has depth as well. This is actually now a four-dimensional, truly four-dimensional representation. So this thing here you can imagine as being a ball. Now what we've got is we've taken this basic 3D object, which is being represented by the green wave. And what that is this tube now that has been bent around, and we're creating something called a torus. So you've got a donut shape. Now that has got a spin. At the minute I've represented it as a clockwise spin. Now if we bend that all the way round, then what you'll find is on the other side, you've got an anti-clockwise spin. And we've created this vortex motion where all the matter on the inside is moving down and all the matter on the outside of this is moving up. We could extend this out to make something that would actually look an awful lot like a magnetic field that you see around any bar magnet or an electromagnet. And what we've also done, now we've got this tube that has got this inward spiraling motion, drawing material or more medium in through the centre of it. We can then also spin that donut shape, that torus, to create a second axis of motion. So not only is there this tumbling, inward pulling vortex motion, it is also spinning around in a circle. So what does that mean? What actually happens then? How does this form this dense point of charge that we are able to recognise? Well, what you would get is you would get an area of low density appearing above and below and around, where the material was moving in a much larger space and moving faster. This is a fluid medium again, remember. We're not talking about nothingness, we're talking about a fluid electromagnetic medium, or the ocean, or the air currents, however you want to consider it. You've got low density above and below it, and then right in the centre, where all that medium is being compressed to a very dense point, you would get a very high density. If you were imagining this thing moving past and you're measuring the medium through this thing, where this thing is moving, you would first see a point of very low density. Then that would, again, as that material started to slow down on approach to that point of singularity, the highest density, it would approach back to the normal. It would then go to a second extreme where the singularity is passing, that's where the highest density is, and then again it would return back to normal, and then eventually low pressure, low density. So there we are. What we've got is two different ways of looking at the same phenomena. You can look at the waves on the ocean and see the wave, perceive the wave as a mass of water moving in a given direction. But you could also perceive that wave as being a simple oscillation of the fluid which is already there. So the conclusion that we're starting to come to here, guys, is that particles are only really functional in terms of modelling systems, and they're really a result of a perceptual bias when measuring a fluid medium. What we think of in empty space is really a vast sea of electromagnetic potential just waiting to be made into a wave. Thank you very much for watching, if indeed you still are. If you did like the content, don't forget to subscribe, hit the thumbs up and the notification bell set to all. We'll make sure you're always kept up to date with all my content, which is dropped on a Monday, Wednesday and Friday at 8 PM UK time. If you do want to join me and become part of our lawful gatherings, conventions and assemblies of people all around the world ready to replace our corrupt governments with systems of natural law and harmony, then come and join me at northlawfulbank.com. Take care of yourself, guys. Don't forget to stay free, think free, and always, always act free. And I'll see you next time.